Okay, back in our chapter 4.5, and we're a little bit further in our notes now, but we're actually kind of going back and touching on, or you might say reinforcing some concepts from really homework 2 of this chapter, the second homework. So in that section we kind of talked about what position vectors were and displacement vectors and how you could take them and get velocity vectors and then acceleration vectors. Here we're going to talk about how instantaneous velocity and acceleration vectors are represented in vector form. All right, so if an object is undergoing some sort of a path, like say here's an object moving from here to here, all right, along this path right here. Certain vectors drawn along that path can tell you, or I guess I should say, the way a vector is drawn can tell you what the vector actually is. At any one point, the velocity vector, that is v, or you might say the instantaneous velocity vector, it's always in the direction of the object's motion. Okay, so if this object is right here, okay, moving from left to right, you would say that it is kind of moving that way, okay, kind of in line with it. Well, because it is kind of moving in a straight line at that point. But let's say the object was right, I don't know, right here. Okay, well, it's kind of going around a curve. Can you have a curved vector? No, you can't, but the instantaneous velocity would be represented as a line that is tangent to that object's path right there. All right, so if it's on the path, then you can think of it as being tangent to it, if the path happens to be in a straight line. But if the path is curving at any one point, the instantaneous velocity, okay, I'm just going to call it v inst right there, is represented by an arrow that is tangent to the path. Now as for the acceleration, I'm going to change that to blue. All right, the acceleration is interesting because it can point in pretty much any direction. It can be directions other than in the direction of motion, and in many cases that is the case. Now let's just say for a minute that we had a velocity, okay, we'll call it an instantaneous velocity, and we had an acceleration that was applied in that same direction right there. Well, the object is going to increase its velocity in that same direction because it's being accelerated. But if an acceleration is applied to an object that is the acceleration is not directly in line with it, if it's at a different in a different direction than the object is moving, then what that means is that acceleration is going to affect the path of that object. In fact, the reason this object is curving right here is because there is an acceleration applied to it that is off axis of the direction that the object is moving. Like I said, we had this tangent line right here, and if nothing else happened, it would go on in a straight line forever. But this acceleration is being applied to it kind of towards the inside of that curve, causing it, in fact, to bend around that curve right there. All right, so the change in velocity is, I feel like I need another color, but well, you could say that the acceleration is directed in the change in velocity. All right, but the instantaneous velocity of the object makes it want to shoot off in a straight line. Okay, we have accelerations applied off axis that changes the direction and changes the velocity, which velocity being a vector, by definition means that it's going to be changing because the direction is changing. All right, so depending on what the angle is, the off-axis angle between acceleration and velocity, that will determine what happens to the velocity. And so there's going to be a chart on the next slide that kind of takes us through what is going to happen if we have a velocity and an acceleration that is off-axis. All right, so let's take a look at this here. All right, if we have, I think we did a velocity in green, okay. There's a velocity. Ooh, you can barely even see that there. And we have the acceleration that is on the exact same axis. That is, the angle between them is 0. And that means that the object is going to speed up, right? The velocity is going to become greater. Is the direction of motion going to change? No, because the acceleration is not off axis. It's just going to keep going in the same direction right there. All right, what's this all this mess right here? Well, this is really saying that, okay, what if the angle between the velocity and the acceleration is somewhere between 0 and 90 degrees? Okay, it's not at right angles to it, but it's at some sort of an acute angle right here. Okay, here's our velocity, here's the acceleration. It's going to speed up because some of this acceleration is applied in the x component, or the x direction right here, or the same direction that the velocity is in. It's going to speed up, but it's going to turn, that is, the path of the object is going to turn towards the direction of A. So while at this point it was moving in a straight line, once the acceleration is applied to it, it's going to start bending around like that. All right? What if the acceleration is at right angles to the velocity? There's our velocity, there's acceleration. It's not going to change the speed at all. The speed will stay constant. Because look, that should be an A right there, sorry. The A is neither contributing to nor hindering the motion of V. It's at right angles to it. So it's not affecting positive or negative the velocity, but what's going to happen is the velocity is going to turn towards A that way as well. All right, what if we have a velocity and we have an acceleration applied to it that's somewhere between, that is, the angle is somewhere between 90 degrees and 180 degrees. Let's say it's like that. Okay, now look at this. If our velocity was, oops, I didn't label it. Velocity was in this direction right here. Now look, the acceleration is acting against it. All right, it's acting in the somewhat in the opposite direction. So therefore, your velocity is going to slow down. It's going to get less and less. Even so, since it is off axis from the velocity, the object is going to turn towards that direction of the acceleration. All right, the velocity direction will change, even though the velocity is slowing down. The direction will change as well. It's going to move towards that acceleration. And finally, what happens if we have a velocity and we have an acceleration completely in the opposite direction right here? All right, you could probably figure this out. We've had problems like this before, where here's our initial velocity, and if the acceleration is applied to it in the absolute opposite direction, it doesn't change at all. It doesn't change the direction at all, but it changes the magnitude of this velocity. So this acceleration, or you would probably call it a deceleration, is going to cause this velocity to get less and less and less, and probably wind up turning around at some point and going the other way. All right, so these are all things that can happen if we have accelerations applied to an object's velocity, and that can affect the object's value, its magnitude, but also its direction as well. The next example on the next slide, I'm going to save for a separate video, but I want to skip through it real quickly. This should say example 4.5. All right, well, never mind, that's going to change anyway. That should be 4.5-7. All right, that should be that name, and I'll change it for the next video. We're skipping over this. We're talking about a car going around a curve. That'd be the problem but we've been talking about all these different kinds of vectors right here, and specifically velocity and acceleration. All right, so velocity is in green, acceleration is in purple right here. And so if we got a velocity right here and the acceleration is applied to it in the absolute opposite direction, what's going to happen? It's going to slow down. All right, it's going to slow down in the direction that it was going, and maybe even start going in the opposite direction towards acceleration. How about right here? All right, acceleration is directed at completely right angles to the initial velocity. So the velocity won't change, but the path that it's taking will change. So change path. All right, same thing up here. All right, we've got a right angle relationship between velocity and acceleration, and as long as you got a velocity in this direction and acceleration directed towards the center, that is going to change the path so that it will follow around towards the acceleration. So the velocity magnitude won't change, but the direction will. Okay, and what if we have a velocity right here and an acceleration in the same direction? Well, it just means that the velocity is going to get greater and greater and greater in that direction right there. It's like the acceleration is helping the velocity become greater and greater magnitude. And since it's in the same direction, it's going to be in the same direction as the initial velocity. So, this is all the relationship between acceleration and velocity, and hopefully you'll be able to pick out patterns like this as we see what happens in the next example, which is going to be example 4.57, which is going to be in the next video. Thanks, and I'll see you next time.